Welcome to The Explainer. Today we're going to tackle two of the most fundamental ideas in all of electronics: the push that gets electricity moving and the pull or friction that keeps it under control. Okay, so let's just jump right in with the biggest question of all. We know electricity flows through wires to power our lives, but why? What is the actual force that makes all those electrons get up and go in the first place?
Well, the answer is a concept called electric potential. And to really get our heads around it, we're going to start with a super simple analogy from the everyday world.
I mean, it's just gravity, right? A ball at the top of a hill has a lot of potential energy, and it naturally wants to roll down to where it has low potential energy. Well, believe it or not, electric charge works in almost the exact same way. It always moves from a point of high electric potential to a point of low electric potential. That difference is the push.
Now, here's a super important distinction we need to make. On one hand, you have electric potential, which is this big, kind of abstract, theoretical idea about bringing a charge from infinitely far away. But what we actually care about in a real circuit is potential difference. That's the measurable energy it takes to move a charge between two specific points, like from the positive to the negative terminal of a battery.
And of course, there's a beautifully simple formula for this. The potential difference, which we represent with a V for volts, is just the amount of work you do, W, divided by the amount of charge you're moving, Q. You can really just think of it as the energy per charge.
So that brings up a good question. We talk about volts all the time. A 9-volt battery, a 120-volt outlet. But what is 1 volt? What does that unit actually represent? To figure that out, we just need to look at the pieces of that formula.
Okay, first let's talk about work, which is measured in joules. Imagine the amount of energy it takes to lift a small apple about 3 feet straight up off the ground. That's roughly 1 joule of work.
Now, take that little bit of energy and imagine using it to push a specific amount of electric charge. That amount is called 1 coulomb. And let me tell you, it's a huge number of electrons. We're talking about 6.24 quintillion of them. It's just an insane amount.
And that's it. That's how it all clicks together. 1 volt is simply the potential difference you have when you use 1 joule of energy to move 1 coulomb of charge. It's our fundamental unit of electrical push.
All right, let's move on to the next piece of this puzzle. So we've got the push. That gets charges moving. But if that was the whole story, electricity would just flow uncontrollably, right? You'd have short circuits everywhere. So what's slowing it down? What's the friction in this system? Think about it like this. You're running down a nice, smooth, clear path. It's pretty easy. But now imagine that same path is suddenly covered in a bunch of loose stones and pebbles. You're not going to stop running, but you're definitely going to slow down. That's a perfect way to think about what resistance does to an electric current.
In an electrical circuit, that path full of stones is a property called resistance. It's literally caused by the flowing electrons bumping and crashing into the atoms of the wire material. And, you might think resistance is a bad thing, but it's absolutely crucial for controlling electricity and making sure our devices work the way they're supposed to.
So, to map all this out, electricians and engineers use a kind of visual shorthand, a set of standard symbols to draw circuit diagrams. Here are some of the heavy hitters you'll always see. The battery provides the push, the switch opens and closes the circuit, and that little zigzag line? That represents a resistor, a component whose whole job is to deliberately add some of that electrical friction.
Okay, so we've got the push, that's the potential difference. And we have the obstacle, that's the resistance. So the big question is, how do these two things actually relate to each other and to the current that ends up flowing through the wire?
Well, luckily for all of us, a German physicist way back in the 1820s named Georg Ohm became obsessed with this very question. And he discovered a simple, incredibly elegant rule that connects them all. It's so important that we named it after him, Ohm's Law.
So what does directly proportional even mean? Well, it sounds kind of fancy, but it's actually dead simple. It just means they're tied together. If you double the push, the voltage, guess what happens? The current also doubles. If you cut the voltage in half, the current gets cut in half too. As long as the resistance stays the same, they move in perfect lockstep.
And this relationship gives us the absolute master formula for basic circuits. V equals I times R. Voltage equals current multiplied by resistance. Seriously, with this one little equation, you can calculate any of those three things if you just know the other two. And you can see here, resistance R is measured in a unit called ohms, a little tribute to the man himself.
All right, that formula is great, but let's get back to the real world. What actually determines the resistance of something like a piece of copper wire?
What makes one wire have more resistance than another?
It really boils down to 4 main things, and honestly, they all make pretty intuitive sense. First, length. A longer wire is like a longer obstacle course, right? So more resistance. Second, thickness. A thicker wire is like a wider highway, making it easier for current to flow, so there's less resistance. Third is temperature. When atoms get hot, they vibrate like crazy, getting in the way of the electrons even more. And finally, of course, the material itself is a huge factor.
And this right here is exactly why we choose certain materials for certain jobs. Sure, silver is the best conductor on the planet, but could you imagine the cost of wiring your house with it? No way. Something like iron, on the other hand, has pretty high resistance and just wastes energy as heat. And that's why copper is king. It hits that perfect sweet spot, incredibly low resistance, but affordable enough to use just about everywhere.
So let's end with a final thought to tie all these ideas together. We now know that as a wire gets hotter, its resistance goes up. So picture a motor in a blender that starts to overheat. What's happening inside? The resistance in its copper windings is skyrocketing. This extra resistance starts to choke off the flow of current, and if the motor can't get enough current, it can't do its job, and eventually it just stops working. By understanding the push and the pull, potential and resistance, you can really start to figure out the electronics all around you.